this week, welcome to the Bare Metal Cyber CISSP Prepcast. This series helps you prepare for the ISC Squared CISSP exam with focused explanations and practical context. In this episode, we explore fault tolerance, redundancy, and high availability. These three concepts are often grouped together because they serve a shared goal, keeping systems running even when things go wrong. Every organization relies on continuous access to applications, data, and communication systems. If those systems go down, even for a few minutes, the impact can be financial, operational, reputational, or worse. Understanding how to design and manage systems that remain resilient in the face of failure is a core competency for every cybersecurity leader. Let's begin with fault tolerance. At its core, fault tolerance is the ability of a system to continue functioning despite the presence of faults or failures. These faults might include hardware malfunctions, software errors, or even unexpected inputs that cause a process to hang or crash. Fault-tolerant systems are designed not just to recover after a failure, but to detect the problem, isolate it, and continue delivering the expected service without any visible disruption to the end user. This is achieved through careful system design. Components are monitored constantly. If a fault occurs, redundant elements can take over the workload. The system may automatically reroute traffic, shift processing, or restart services without needing human intervention. For example, a fault-tolerant web server cluster might detect that one of its nodes is failing to respond. That node can be removed from the pool, and the remaining servers will continue to handle incoming requests without interruption. Fault tolerance is not an accident. It is the result of deliberate architectural planning. It requires visibility into the system, intelligent automation, and extensive testing. It also requires attention to component compatibility and failover coordination. Systems must know what to do and how to behave when things start to go wrong. Next, let's examine redundancy. Redundancy is one of the building blocks of fault tolerance. It refers to the duplication of critical components so that there is always a backup ready to take over in case the primary component fails. Redundancy can be implemented in multiple ways. Hardware redundancy might mean having multiple servers, hard drives, or network interface cards running in parallel. If one component fails, the redundant one automatically takes over. Network redundancy might involve multiple internet connections or alternative routing paths that maintain connectivity if one link goes down. Data redundancy might involve mirror databases or synchronized storage arrays that ensure a real-time copy of important data is always available. You might also see power redundancy in the form of uninterruptible power supplies, battery backups, and on-site generators. If the primary power source fails, the system continues running without disruption. The goal of redundancy is to eliminate single points of failure. If a system depends entirely on one server, one network switch, or one data center, then any issue with that component can bring down the entire service. Redundancy spreads risk and increases the likelihood that service will remain available even when components fail. But redundancy is not a guarantee. It must be tested, monitored, and maintained. Backup systems must be kept in sync. Failover mechanisms must be verified. If a redundant server is configured incorrectly, it will not help when the primary fails. If a power backup system is not tested regularly, it may not kick in when needed. Redundancy is only as reliable as the controls and oversight around it. Now let's look at high availability. High availability is the outcome we're aiming for when we implement fault tolerance and redundancy. It is the ability of a system to remain operational and accessible over a sustained period, even in the face of disruptions. High availability is often defined in terms of uptime, such as 5 nines, which means the system is available 99.999% of the time. That translates to just over 5 minutes of downtime per year. Achieving this level of availability requires more than just redundant hardware. It requires load balancing to distribute traffic efficiently. It requires clustering to ensure service continuity. It requires robust monitoring, fast detection, and automated failover. Disaster recovery planning is also a major component of high availability. If an entire data center goes offline, can services be restored quickly from a secondary location? Are there procedures in place to switch workloads to a different region? Are backups recent, complete, and readily accessible? Achieving high availability is not just about hardware, it's also about people and processes. Regular maintenance is essential. Patches must be applied without disrupting services. Monitoring tools must be tuned to detect and report problems before users notice. Response teams must be trained and ready. For more cybersecurity content and books, please visit cyberauthor.me. You'll find bestseller books, training tools, and resources tailored specifically for cybersecurity professionals. You can also find more study support at baremetalcyber.com. Let's now examine how to implement effective fault tolerance and high availability controls in the real world. The first step is clear documentation. Your organization must have policies and procedures that specify how fault tolerance is achieved, how redundancy is maintained, and how high availability is measured and monitored. Use clustering technologies to group servers into a shared processing pool. If one node goes down, others take over the load. Use load balancers to distribute traffic intelligently across multiple servers, reducing strain on any single component. Use automated failover systems that detect problems and switch to backups without human intervention. Data protection is another critical area. Backups should be performed frequently and stored securely in multiple locations. Use replication to maintain synchronized copies of data across different environments. Make sure you have restore procedures that are fast, tested, and reliable. Redundancy components must be monitored. Just because something is redundant does not mean it is always functional. Monitor system health, synchronize data, and log all failover activity. Schedule maintenance checks to verify that redundant systems will activate when needed. Disaster recovery tests must be conducted on a regular basis. These are not theoretical exercises. You must simulate real-world disruptions and test your ability to maintain or restore availability under stress. This helps uncover hidden dependencies, outdated procedures, or overlooked single points of failure. Let's now look at the need for continuous improvement in resilience management. Operational resilience is not a one-time investment. It is a long-term commitment that evolves with your environment, your business requirements, and the threat landscape. Start by reviewing incidents. If a system experienced downtime, ask why. Was the failure detected promptly? Did the redundant component activate properly? Did users notice the disruption? Use these lessons to adjust your architecture, update your procedures, and improve your alerts. Audit your systems regularly. Are failover links still functional? Is redundant storage still synchronized? Have recent patches introduced unexpected changes to your availability strategy? Use audits to verify that your systems perform as designed. Collaborate across departments. Resilience involves more than just the IT team. Business units must help define acceptable downtime thresholds. Legal teams must ensure that service-level agreements are realistic and enforceable. Security teams must validate that redundancy and failover systems do not introduce new vulnerabilities. Training is vital. Your staff must know how to respond when failover occurs. They must know how to troubleshoot high availability clusters. They must understand how to escalate unresolved issues and how to recover from major outages. Finally, take a proactive stance. As new technologies become available, like software-defined networking, edge computing, and container orchestration, look for new opportunities to improve availability. As threat actors evolve their tactics, adapt your defenses. As regulations change, update your compliance posture. Remember, availability is one of the foundational pillars of cybersecurity. Without it, even the best confidentiality and integrity protections cannot fulfill their purpose. Fault tolerance, redundancy, and high availability are how we ensure that users have access to the systems they need when they need them, regardless of the challenges we face. Thank you for joining the CISSP Prepcast by Bare Metal Cyber. Visit baremetalcyber.com for additional episodes, comprehensive CISSP study resources, and personalized certification support. Deepen your understanding of fault tolerance, redundancy, and high availability, and will consistently support your journey towards CISSP certification success.